In section 8.3, we are going to be solving trigonometric equations. We're going to solve some simple ones that just have one trig function in them. We are going to learn how to use our calculator to solve some. We're going to solve trig equations that are quadratic in form, so you can kind of think about ahead what those might look like. Sine squared of theta plus the sine of theta plus a constant, and then think about how you might do a u substitution. We're going to use some of the fundamental identities that we've already talked a little bit about, and then we're going to look at how to solve these kinds of equations with our calculator. So we're not going to do the first example together. It's pretty straightforward. They want you to figure out if pi over 4 and then if pi over 6 are solutions to this equation. So you would substitute each of those in for theta, figure out what this is equal to, and simplify to see if you have solutions. Example 2 is also pretty straightforward. You'll notice that I put a little unit circle here to help you out. Remember that you're supposed to be memorizing those values, and I think the more you look them up on the unit circle, the easier they become to remember. What we're looking for in this equation are values of theta. So we're looking for angles whose cosine is a half. So in our unit circle, we're looking for points whose x-coordinate is a half. The directions say to give a general formula. So they're looking for us to have solutions that go clockwise, go counterclockwise, and that go more than one revolution. And they want us to list 8 solutions. So this problem really wants to see whether or not you understand that repetition of the unit circle. So if we look at our unit circle, one of the places where our x-coordinate is equal to a half is at pi over 3. And then our x-coordinate is also equal to a half at 5 pi over 3. So we're going to have other solutions at multiples of those numbers, that like numbers that are 2 pi more than those numbers. So we can kind of think of our solutions in 2 sets. So pi over 3 is going to be a solution. And then anytime we add 2 pi, which is 6 pi over 3, we're going to come up with another solution. So pi over 3 would be a solution, 7 pi over 3 would be a solution, 13 pi over 3 would be a solution. We could also go in the negative direction, and so if we started at pi over 3 and then we subtracted 6 pi over 3, we would end up with 5 pi over 3, which is the other solution we got in the unit circle. If we subtract it again, we would get negative pi over 3. We could subtract it again, and we would have negative 7 pi over 3. So if we want to list all those solutions, we start with the ones that are actually in the unit circle. So pi over 3 plus k times 2 pi and 5 pi over 3 plus k times 2 pi, where k is an integer, is the general form for all solutions. So that gets us the solution where you have repeatedly gone around and around the unit circle. I'm going to move that unit circle down here with me, I hope. So many of these problems you're going to approach the same way you approach an equation that just has an x in it. Think of your theta as your x. So in this case, we're going to try to get sine of theta by itself. So if we have 2 sine of theta plus root 3 over 2 equals 0, I'm going to subtract that root 3 from both sides. So I've got 2 sine of theta equals negative root 3. I'm going to divide both sides by 2. And I've got sine of theta equals negative square root 3 over 2. the directions to this problem, look at the inequality symbols very carefully. We're looking for solutions that are less than or equal, or I'm sorry, that are greater than or equal to 0, but that are strictly less than 2 pi. So if 2 pi would happen to be a place where the sine of theta is negative square root 3 over 2, that would not be a solution because it's not on the interval that they ask us to solve the problem in. So if we look at our unit circle, remember that we're looking for places where the y-coordinate is equal to negative square root 3 over 2. Those are going to be in the bottom half of the circle. And so here is one down here at 4 pi over 3. That's kind of hard to see, that tiny little thing, isn't it? And then there's another one right here at 5 pi over 3. So we only have 2 solutions in the interval that we're interested in, and those 2 solutions are 4 pi over 3 and 5 pi over 3. Example 4 is an interesting one because this time something has been done to the theta inside of the function. We're still looking for solutions on the interval from 0 to 2 pi. And I'm going to think about this with u substitution. So I'm going to say, okay, well, I'm going to let u be equal to 2 times theta. So I want to solve the sine of u equals a half. So I'm looking for places in my unit circle where my y-coordinate is equal to a half. So that's going to happen at pi over 6 and 5 pi over 6. Okay, so right here my solution is going to be that u equals pi over 6 and u equals 5 pi over 6. But I'm not finished yet because I haven't solved for theta. So I'm going to replace u with 2 theta. So 2 theta equals pi over 6. If I divide both sides of this by 2 or multiply both sides by a half, the 2 goes away, and I get theta equals pi over 12. If you think about putting that back into the original problem, that would be the sine of 2 times pi over 12, which would be the sine of pi over 6. And sure enough, the sine of pi over 6 is equal to a half, which is what we're looking for. We're going to do the same thing with this one. So we're going to have 2 theta equals 5 pi over 6. Going to multiply both sides by a half, and theta is going to equal 5 pi over 12. Now we got to be careful here because we might have, when we did that last step, we might have found solutions that were outside of the interval that we're looking for. So just double check. Is pi over 12 bigger than 0 and less than 2 pi? It is, as is 5 pi over 12. So those solutions are in the interval where we were looking for solutions. What we haven't considered yet is whether or not we have found all the solutions in this interval. We want to go back and look at our function and remember that the period is 2 pi over b. So in this case, our period is going to be 2 pi over 2, or pi. Think about what period means. It means that the function is going to repeat itself every pi units. So if we have a solution at pi over 12, we're going to have another solution at pi over 12 plus pi. But I want to think of pi as 12 pi over 12. So that's going to give me a solution at 13 pi over 12. Okay, I'm going to pause for a minute and think about, if I have a denominator of 12, how am I going to know if I have passed 2 pi? Right, so 2 pi is going to be equal to 24 pi over 12. So I don't want anything that's bigger than this. So if I add another 12 pi over 12 to 13 pi over 12, that's going to be 25 pi over 12, and that's too big. but I could still have other solutions up here with 5 pi over 12. If I start with 5 pi over 12 and I add 12 pi over 12, that gives me 17 pi over 12, which isn't too big, but then adding another one would. So this function actually has 4 solutions. Theta is equal to pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And remember, what we did to find those extra solutions was to find the period of the function and then add that period to our solutions until we got outside of the range that the problem was asking us to solve within. I am once again going to use substitution to solve this equation. We've got the tangent of theta minus pi over 2 equals 1. We're going to let u be equal to theta minus pi over 2. And so we're looking for the tangent of u to be equal to 1. We know that in the interval from 0 to 2 pi, tangent is going to equal 1 here and here at pi over 4 and at 135 pi over 4. So we're going to let u be equal to pi over 4. We have u equals pi over 4 and 5 pi over 4. We have to substitute theta minus pi over 2 back in for u. So theta minus pi over 2 equals pi over 4. If I add pi over 2 to both sides, hold on. If I add pi over 2 to both sides, I have to get common denominators. So theta equals pi over 4 plus 2 pi over 4, which is 3 pi over 4. For my other solution, theta minus pi over 2 equals 5 pi over 4. I'm going to add pi over 2 again, which is 2 pi over 4. So I've got 7 pi over 4. There's no number in front of the theta, so the period of tan is pi. 3 pi over 4 and 7 pi over 4 are both inside that range. We look at our denominator of 4. 2 pi is equal to 8 pi over 4. If I try to add pi to this solution, that would be 4 pi over 4. That would be outside of the range. If I add 4 pi over 4 to this solution, that takes me to 7 pi over 4. So those are our only two solutions in the domain that they gave us. You want to be really careful, because the problems that you can use your stat calculator to solve, I think, tend to be the most complicated ones. So what we want to do on this one, we're trying to find the angle where the tangent of theta is equal to -2, and we're looking for solutions to that that are between 0 and 2 pi. And because we're using our calculator, you might want to think about this interval as being between 0 and approximately 6.28. So if you take tangent inverse of both sides of this, remember that your calculator is going to give back to you values of tangent that are in between -pi over 2 and pi over 2, which doesn't match where we're looking for solutions for in our problem. So we're going to have to be careful and do some adjustments to our answer. So if I do tan inverse of both sides, then this gives me theta. And the tan inverse of -2 is about -1.11. We want to be accurate to 3 decimal places, so wait a second while I do this on my calculator. I get -1.107 if I round, and if I don't round, maybe if I keep a few more decimal places, 148718. There's a whole lot more decimal places. That solution is an angle that we go in the negative direction to get. And so I know that this is a tangent function and that the period of the tangent function is pi. And so if tangent is equal to -2 when my angle is -1.107, then it will also be equal to that in pi units. And so what I could do is simply add pi to that number. So if I add pi to it the first time, I get 2.034444. So if I round to 3 decimal places, I got 2.034, and that is in the domain that the problem asked me for a solution in. If I add pi to that number again, I get 5.176, which is also in the domain that the problem gave. If I add pi to it again, remember pi is about 3.14, I'm going to be bigger than 6.28. So these are my 2 solutions to this problem. Example 7 is one of my favorite kind of problems. This is something that is quadratic in form. And you can kind of see it. You got a sine squared, you got a sine, you got a constant. It's the whole thing's equal to 0. I think u substitution can be helpful. I am going to let u be equal to the sine of theta. And so I'm going to have 2 times u squared minus 3 times u plus 1 is equal to 0. I am going to hope that this factors. Let's see, 2u and u. I need a minus 1 and a minus 1, I think, so that'll give me minus 1 and minus 2. Yep, that works. So if 2u minus 1 is equal to 0, or u minus 1 is equal to 0, then u is a half, or u is 1. But I have to do my substitution. So I'm looking for places where the sine of theta is equal to a half, or where the sine of theta is equal to 1. If I think about my unit circle, my y-coordinate is equal to a half, let's see, here, and here, and it's equal to 1 up here. So it looks like theta is going to be equal to pi over 6, pi over 2, and 5 pi over 6. I don't think there's any place else between 0 and 2 pi where sine is equal to positive 1/2. So that should be all of our solutions. So example 8 should kind of be talking to you and saying, hey, I look like I'm quadratic in form, but there's a problem because, wait, there's a cosine here and there's a sine squared there, so that doesn't quite work. So what we have to do is use one of our identities. And so what we're always trying to do is to get our function in terms of just one trig function. So I got to figure out what the best way is to do that. I know that sine squared of theta is equal to 1 minus the cosine squared of theta, because that's just a rearrangement of the Pythagorean identity. And so that, to me, seems like that would be a place to go that wouldn't give me square roots and craziness. So I got 3 times the cosine of theta plus 3 equals 2 times, and then this is where I'm going to substitute, 1 minus the cosine squared of theta. And then I'm going to distribute that 2 and bring everything to the left eventually. So I've got 3 cos theta plus 3 equals 2 minus 2 times cosine squared of theta. So if I bring that over to the left, I've got 2 times cosine squared of theta plus 3 times the cosine of theta plus 1 equals 0. So I could use u substitution again. That would be 2u squared plus 3u plus 1 equals 0. This is almost exactly the same factors as before. I think this is 2u plus 1 and u plus 1 equals 0. And I'm going to let you solve it from there because it's just like the one that we did above. I'm going to let you read example 9 for yourself because it is very much like what we just did in examples 7 and 8. In example 10, when we're solving by graphing, what we want to do is to let each side of our equation be a function in our calculator. So we're going to graph y equals the 5 times the sine of x plus x, and we're going to let y equals 3, and then we are going to look for the places on our graph where there are intersections. And we use the intersect feature on our calculator, and that gives us our 3 solutions. Sometimes you're going to have to be careful about your window, so just kind of pay attention to what your values look like and set your window up from there.